Hello, thanks for joining. I'm Chris Martis, I'm the Solutions Director of Grid13, and today we're going to discuss the topic Actuarial Modeling at Crossroads. We're going to cover a few topics, particularly GPUs, but we're also going to talk about AI, open source, and the future of code, or more about the evolution of code. We're going to explore how these technologies and new paradigms are shaping the life actuarial platform industry, but from a vendor's point of view. But let's go through some antitrust laws. We have to adhere on this guidance. So basically, we have to avoid discussions about pricing, no market allocation, refrain from discussing any plans about geographic or product markets, any conversations about membership restrictions, product standardization, and obviously feel free to leave if necessary if any of this discussion you feel are violating any of these guidance. Next, some thanks and disclaimer. Thanks to Full Stack Actuarial and all the sponsors who made this possible. And it's also worth mentioning that any views expressed in this session and all the other ones obviously do not necessarily reflect a position of all the employers, Full Stack Actuarial, the conference sponsors, or any other entity associated with them. So today, in particular, we're going to take a journey and cover a few topics. First of all, we're going to spend a lot of time talking about the GPU architecture. We're going to be discussing about the foundation of the hardware, the component relationship, and how this is affecting actuarial modeling and what is difficult about it. We're also going to discuss performance reality about the claims on the GPU performance. Then we're also going to talk next on AI power transformation, so how AI could be used in actuarial modeling. Then we're going to talk about the open source economics. So we're going to weigh the visible and the invisible benefits and costs. Then I'm going to cover about the discussions around like low code versus verbose approaches, particularly as things like vibe coding are becoming more prevalent. And then going to discuss a bit about how we approach a couple of these things about these topics. So without further ado, about the reality, the problems in the reality. So basically, a lot of people believe, when you look at the GPU architecture, there's thousands of cores, 6,000, even 10,000, a lot more in more recent iterations. And the mathematics seem to be quite straightforward. If I've got 6,000 cores, if I compare with a CPU which takes 100 hours, surely 6,000 cores should complete it in a minute. And there is a linear scaling assumption that guides many initial GPU adoption views in actuarial departments worldwide. Now, in practical experience, though, you'll find that practical GPU solutions typically observe speedups compared to a good CPU vectorized efficient solution, more in the 15s and maybe up to perhaps 300, which is definitely impressive, certainly, but it's not really 6,000. I mean, obviously, you can get examples where this is true, but then are you comparing against the maximum possibility of the hardware or not? Now, to understand this gap between the actual and the expected, we have to start examining a bit about the GPU architecture specifically, and then talk about how memory is handled, and how the nature of the actuarial computations fit into the world of GPUs and the hardware, and also how do you navigate some of these limitations, because there are limitations on the hardware. There are also limitations on the actual things that we want to do with the hardware, and there are also limitations in the expressions, or a lot of people believe so. So let's dive into the GPU architecture. So in order to understand all the limitations, we must really dive into how GPUs actually work. So, I mean, this is something that you probably already heard. Unlike CPUs, where the emphasis is on processing sequentially instructions, the GPUs sacrifice individual core sophistication for scale parallelisms. So what this means is that they have simpler cores, not as powerful, but they've got a lot more of them. And they actually share the memory in a slightly different way. So when you're working with GPUs, the art of this is to keep the cores as busy as possible for as long as possible without introducing bottlenecks. So basically to achieve as much parallelism as you can. Now, diving into the history of GPUs, should be worth noting that GPUs were initially built for graphics, and now they're used for AI. Now, in both use cases, these have completely different characteristics than what you would encounter in a typical life insurance calculation kernel. Okay, so although actuaries can benefit from the architecture, and definitely there are some benefits into actually doing it to GPUs, you have to accept some of the limitations. Now, there is also some misunderstandings that you may hear, like, if I've got 20 gigabytes of RAM across 5,000 threads, that means I only have 5 megabytes per thread to play with. 5,000 cores means 5,000 times faster. And, the reality is it does not work like that. And that will be apparent in some of the rest. The first thing that we need to understand is some concepts around GPUs. Okay, so we're gonna discuss some of them here. Which are the key ingredients that you're playing with when you actually have a kernel. A kernel is basically the calculation unit inside your code. So basically, you launch a kernel into the GPU does all the work. Now, the most fundamental unit and the smallest unit of execution is a thread. So each thread runs a single instance of your core calculation logic, the kernel. And you can have a GPU is very good at handling millions of them simultaneously. And also, as we said before, each thread is quite lightweight, and it can only access its own kind of memory environment called registers and some shared memory. Now, threads are organized next into what is called warps. So you've got warps of 32 threads. We're talking about NVIDIA here, right? So NVIDIA groups has 32 threads into warps that execute alongside using a single instruction multiple thread architecture. So this is very, very crucial. Basically, you want to repeat across all your threads. That is how you approach parallelism. So this is when you probably heard that it says, you shouldn't have branching. Now, what branching does, it means that the kernel at some point finds a branch, and some threads within threads have to do some things, and some have to do another thing. In this case, these are going to be queued one after the other. So then, depending on the divergence and the relative split across your whole job, that can significantly degrade your performance. This is a quite important bit to solve, an important problem to solve. AMD has a slightly different way of expressing things, but obviously CUDA is what I know and what I'll talk about here. Now, next you've got thread blocks. So it's logical grouping of up to 1024 threads that can communicate with shared memory. So blocks are assigned within the streaming multiprocessor. We'll discuss this in a bit. and can be organized, in 1, 2D or 3D blocks. So basically, you can actually think of them in different ways of how you can actually allocate them within your problem structure, the grid. We'll discuss this a bit later. Another fundamental bit of your architecture of GPU is registers. So these are the very high speed, very close to the core storage, and it's private to each thread. So each thread gets a set of registers, so 32-bit or 64-bit, and that is what they actually use to play around with the data. So NVIDIA GPUs have a large register file per streaming multiprocessor. We're going to discuss SMs in a bit. So basically, you get about 64,000 32-bit registers per streaming multiprocessor. Now, still limiting, shared among threads, and registers are allocated at compile time. So the structure of your code will affect the usage of register. And this is probably the single, in my view, most important thing about your kernels. So basically, it's how you can actually make efficient use of your registers. Because if not, then nasty things happen and things slow down. Now, another fundamental building block is your warp scheduler. Now, these are hardware units within each streaming multiprocessor that manage warp execution. So basically, within an SM, which is a collection of cores, really, you allocate warps which contain threads. So basically, the whole point is that you've got the warp scheduler that does all the jobs. So in the more recent architecture, you've got 4 inside HSMM, its streaming multiprocessor, and it's handling a subset of the warps. So they select warps which are ready to launch, they issue instructions to the cores and switch between warps. So another important bit is you cannot influence this directly, but you can influence it indirectly. So if you've got what you got occupancy, high enough occupancy, you can keep the warp schedulers busy. So while some are doing work, the other ones collect results and prepare them and so on. Now, the next bit is cores. So this is, very similar to what you know from other architectures. So within a streaming multiprocessor, you've got cores, and each SM has hundreds of CUDA cores. So for example, 128, if you look at them here. So they handle integer and floating point operations. That's why you hear that a string is avoided in GPUs. Some of them ban compilability. And there's another type of cores, which are called tensor cores. And they are very focused on AI matrix multiplication kind of calculations. Even recently, you might have heard about Google, who actually use their own TPUs. So these are specialized cores that are very good at doing this kind of matrix multiplication calculations. Now, these are not general purpose cores, and they're not of much use to general life insurance calculations. There could be some bits that you may want to use them, but fundamentally, these are the ones that are geared for AI, but these are the ones who actually are not that useful for us anyway. Okay, so there is kind of hierarchical organization where you got threads on one end, you've got cores on the other end, and you've got some way of managing this in the middle, whether it's blocks, whether it's warps, whether it's registers within the cores, whether it's warp schedulers. All of these interact with each other during the work that you have to do, and each of them pose their own limitations. Now, more detail now about the SMs. So this is the GPU workhorse. So basically, these are the fundamental building blocks of a GPU, and essentially are mini processors within a larger chip. Okay, a high-end GPU like the RTX 4090 contains 128 SMs, each capable of executing thread blocks independently. Within the blocks, remember, you've got warps, you've got threads. So Each streaming multiprocessor contains hundreds of CUDA cores, multiple word schedulers, we saw earlier, typically 4 per SM, a large register fine, and some cache memory. So basically, it's your buffer of the memory. And this self-contained design enable the true parallelism in GPUs. Okay, so if you look at the big picture, you've got 48 to 132 SMs in a GPU. You've got between 64 and 128 cores per SM. Depends on which generation of GPUs you got. Ampere, you got Ada Lovelace, we got Hopper, and then you got 4 warp schedulers per SM. Now, there is a coordination challenge. So we talked about earlier why 6,000 cores will not give you 6,000 speed up. So as we said earlier, the way GPUs have been built have more been built for AI kind of work. And also we talked about Google and TPUs. So there are resources challenges here that do not fit the actuarial profession. So for example, the limit of the register file, in fact, are not big enough for life insurance models, but they are very, very good and sufficient for training AI. And because obviously there is a biggest market in training AI than it is in actuarial life insurance, that's why we have to navigate these challenges. And that's why, we don't get the 6,000 times speed up, because the limits were not built for our problems. And we only can benefit so much from the architecture. We also see that when it comes to actuarial modeling, you can see some top-end cards, A100, for example, or some middle-of-the-range ones, A4000s and RTX 4000s and so on, or even smaller cards. You can see that the scaling of calculation is not linear. So a 20 times more expensive card doesn't give you necessarily 20 times the speed up. So sometimes you need to maybe think, okay, do I need to get a very, very good card, or do I get 5 or 10 middle of the road one, and I get better scalability? So these are the things that it really depends on. That there's no one rule that one size fits all. You need to actually look at the problem and see how the problem scales. Now, again, looking at the architecture, it's important to look at this pyramid. So the further at the top of the pyramid, the faster the memory and the closer you are to the cores. So the more work you can do at the top of the pyramid in your actuarial kernel, the more time you spend calculating and less time waiting for data to travel between the different levels of the pyramid. So registers at the top. So this is like the fastest RAM, the fastest memory, which is very close to the chip. And that's where you want to be. That's this soft spot. So if you can make your model fit all of it in one, then you're good. So level 1 cache is also very, very fast. Is to store things while you need them across all your threads and so on. So this is shared across the streaming multiprocessor, remember. So this is within the streaming multiprocessor. Then you got level 2 cache, which is across streaming multiprocessors. Remember, you've got many per GPU structure. And then you go global memory, which is available between the host, the CPU and the GPU, but it's obviously, you see it slows quite a bit. So, and also if you look at the registers, you have 256 kilobytes for most, or double that for Hopper. So the bigger the model it is, the fewer blocks you can, because the limit is the same. Okay, and that determines how much how much of the how many blocks you can launch, because a block is a collection of warps. Okay, but then if you launch too many, you run out of registers. So the whole point is to minimize your model size by making it most efficient, to maximize the blocks and be able to spend a lot of time into your registers. So this is quite important. Now, here's just putting it all together. So you've got some typical values on the right. You can go through them yourselves, and on the left you can actually see how things interact. So you've got at the top the kernel launch, and this is a collection of blocks, and its block is a collection of threads. And these collection of threads are sent to the streaming multi-processors. So the schedulers get them, put them into warps, right, which go into threads, and that's all the work done. So the thread schedulers uses multiprocessors, which are a collection of cores, and then you play with level 1 cache and registers. And then you go from the GPU memory on the other side is more talking about, the memory traveling. Okay, so it's a combination between tasks and hardware hierarchy. So it's not a perfect. It's a bit difficult to do a hierarchy, but it just gives you an idea of how things are done internally. Now you don't need to know a lot of this, because a lot of this is done automatically. You can influence certain things, and you can set certain instructions when you launch your kernels. But the whole point is that there are limits in everywhere that you see it, and there's a trade-off when you're in one block, purple or pink, whatever it is, block, then that will have a different impact on your calculation speed. Okay, so on the right here, you can actually see some of the numerical limits of what it means. So if we were to go about, I've got 6,000, why can I not do 6,000? It all starts into how much you can fit into this box, okay? And how much, because you cannot fit into the box, you're in a different box, slows down things, which means then memory bound instead of calculation bound, okay? Talking about performance killers. So if we look at each of the different elements of an actuarial model, then let's look at what it means for your limits. So the memory movement overhead. So actuarial models frequently access large might be running a million sims. If you don't have those million sims inside calculated on the fly, you have to read them from outside. So if it's not a million, it could be like 2,000, 10,000, the same thing. Also, you may be reading like 2 million records or 10,000 records. These have to be coming externally. So you have to swap information, because obviously the limits of the gigabytes of a GPU, normal ones are anything between, 12 and 20. You can get 80 and more on the high-end cards. So there are limits there. So you have to spend some time swapping data from one place to another one, which means you have to wait for things. So there you go. So just for the moving data from one box to another one introduces some latency. So this starts to explain initially some of the overheads that you have when you actually launch a new kernel or move data around, when you have states that you need to save and so on. I mean, there are other techniques that reduce that. So you can use appropriate memory allocation techniques to limit or mask some of the impact that you get. But you remember, you get 255 registers within a register file, which is 127 doubles, something like that. okay, or double that if it's singles. So basically you don't have a lot of, it's even less than 5 megabytes per thread that you're looking at. We're talking about your whole model has to run on these number of doubles. Then you have a lot of reporting requirements. So basically, in AI and so on, it's basically, one value that is interested. You don't need to know the history of the calculations. It's a final answer, so you have like the transformation layers, and then you go into different paths, and at the end is what is the answer. Whereas in actuarial models, you have to keep track of a lot of the path dependence values, time values, group things, but different things. All of these introduce bottlenecks because there's a couple of things that happen here. First of all, you need to maybe write to the same cell across thousands of threads. You may want to output the same time period and sum across all. Now, threads may different policies the same time to write, that has to be serialized. Okay, so that's where you can spend some time waiting. Recent architectures, help you deal with that, but it is a bottleneck. And also, at the end of the run, there is an overhead with writing. Okay, and at the beginning of the run, there's an overhead of reading. So all of these have to be factored, and you have to do it efficiently. So when you run, I don't know, 30 million records, ALM, and you've got like 1,000 SIMs and so on, and you want to write all of that result, where you spend your time and how many times you spend time doing each of the tasks also is a problem. So by carefully managing such interactions, but at the same time avoiding limiting functionality that actuaries are used to, you can actually have a successful kind of implementation. Now, the other thing is, we covered this before. So this is probably related to the memory movement overhead, but one is more on the core level, the other one is more on the data level. Then text string. So people think that GPUs cannot handle text, but and also you can use text, you can do text operations, but they're not as efficient. And considering you've got so much register limits around your GPU structure, that means that you don't want to be wasting it on text unnecessarily. So you need to introduce appropriate infrastructures in order to integrate text. So more successful GPU actuarial platforms do not impose, overzealous data type restrictions and so on. Or, more generally, you don't want to, actuaries are used to moving forward in time and backward in time. So you don't want to start thinking too much in array size. You want to be thinking in actuarial terms, project this and discount it, and I maybe want to go back forward again and do increment in the reserves and so on. So you don't want to introduce restrictions. So the art when you're building, the GPU infrastructure is to still provide something that is very familiar. Next one was model size. We covered this before. So imagine a model with hundreds of doubles or floats, hundreds of arrays of perhaps index of 1,200, dimension variables, 120 values per array. Plus sometimes you want state management across multiple threads. You want them to coordinate. You have loops. You have, as we said before, backwards and forward moving, rebasing, stochastic, nested stochastic, policy loops, all sorts of complications. So the actuarial task is quite big. So the art is to be able to express it in a way that reduces the strain on your registers. And also going back to your actual actuarial model expressions, as we said before, there's a misconception that you have to rewrite your GPU models. Then perhaps in certain platforms you need, some others you don't. We found necessarily need to. It's not generally true. So if you have an array thinking infrastructure, this is not necessarily true. And also in platforms where the what you want to do with the how you want to do it is detached, it's easier to actually find a way to do what you intend to do without having any hardware limitations or expression limitations rather. So some of the limits which we believe are unnecessary is, for example, the time travel thing we said. So, for example, you only have to go forward in time. You cannot use text searching in tables, for example. Everything has to be indexed by position. That's not true. Completely disallow text in data expressions. That's not true. And also repeated run from the start for ALM. So some in some implementations that we've heard of, which we've also integrated, but you don't always need it. So basically, when you want to run all policies for one period, do some calculations, then return that calculation answer back to the rest of the periods and continue. Now, normally you would have to save the state of that calculation step and then move to the next one by using that information and refreshing. Now, this is the reason why ALMs are, in CPU platforms that you've seen in the past, you have to group policies, or maybe you have to do other things like, calibration of surfaces and use, proxy modeling and so on. But we have an example, for example, where we run 30 million records, in a couple of seconds per sim for 4 interconnected models. Two of them having. So you got like the top model and 3 submodels, and one has 500,000 records, the other one has another half, and the last one has 1 million or so on. No, sorry, that's 4 million. And 2 million in a second. And then we ran it also with 30 million by extending that infrastructure. And that again runs in under a minute, so it's still in seconds. So you can do that without actually having to repeatedly run. So, I mean, there are certain models that you may want to do the repeated run. So basically, run everything for one period, take the decision, start from the beginning, go to the next decision, start from the beginning, go to the next one. That means that you avoid all the interaction with the state, but obviously it means that you have n square work, the effort. Right, so now CPUs, I'm going to raise the last couple of slides which cover other aspects that are also relevant for actuarial modeling in this new era of technology. So starting from AI, so there's a lot of information already contained in PDFs, Word documents, scanned images that contain a lot of product literature, for example. And artificial intelligence can offer practical tools to extract and structure that information in a usable way. The trend we see in Actuarial platform is more on code completion, code auto generation, explanation, documentation, spreadsheet transformation, code translation, and so on. However, a lot of the unstructured information that exists, can provide a lot of the source for actuarial modeling. That could actually change the way that we see the problem. So, line one that we've implemented. So here you've got the document ingestion part where there's a variety of LLM tooling that can help you extract and parse text from a variety of formats. Having LLMs trained appropriately can recognize the relevant things for our domain and scale it. Then the process of actually extracting all of that information then leads to metadata in a form that then can be used by the last step, which is the model generation. So in a practical benefit of this approach, in some use cases we had a case where about maybe 7 or 8 big product specs containing hundreds of product variations were processed in under 20 minutes at a cost of, I say under $5, it was probably under $1. Um, and produces a first cut model covering 80% of the functionality. So then this means that the modeling then becomes more of a data and assumption exercise and a model review exercise rather than, a process of actually trying to ingest documentation and bring information into usable format. So obviously the job does not finish there. You need the rest of maybe 20%. Rationalize, finish the edge cases. So a human in the loop is always needed. Now, next topic is about open source. Now, most of the times this is considered as a battle between, vendors versus proprietary versus open source. For me, I see this as to buy or to build, because a lot of the tooling that vendors use is open source. So, or consultants, for example. So the question then becomes, what happens when you buy and build? So basically, it's about outsourcing some of the responsibilities around building. That's what it boils down to. So if we look at it like that, the visible benefits of open source or building yourself is, you don't have license fees. There is a community support allowed the libraries. You have full control and visibility of the actual workflow and the calculations you want to do, and you have flexibility in terms of addressing your requirements in the build, and there's no vendor lock-in, freedom to change direction. So on the flip side of this, when you're actually building yourself, then a lot of the audit responsibilities around the build itself, not the models and the results and the data, but actually the tooling around you building it has to actually be covered by you. So that there is a cost involved with that. Also, when it comes to maintenance and cost, that also will be owned by you. So you have to have dedicated processes that also have to you make sure adhere to vulnerability tests and so on. So there's a host of IT requirements around that. And also if there are support gaps, if you rely on open source, the response times could be different. And also you need staff expertise. Obviously, AI can help you bridge some of these gaps, but they still exist. So regulators in general would not distinguish between proprietary and open source software. There's a lot of common parts that both are going to be needed in terms of validation and so on. When you own a lot of the development, that comes into your internal scope of auditing. And a lot of the vendor solutions, provide already some audit packs and tooling to do this. In the other case, you have to cater for it. So these are all hidden costs that should not be ignored. Now, it's a non-scientific graph. It's not based on any research. It's more my opinion about, the relative cost of different elements when you consider proprietary or open source. So, for example, licensing fees, we cover that. Implementation fees, there's a lot of common elements, but there is that extra element for implementation and audit validation that you internalize that has to come to you. And also some of the audit and validation, of the modeling itself and so on is common. Annual maintenance, again, some of it is common and you need to do it in terms of, the internal infrastructure, maybe of proprietary software, but there is always this extra bit when you own the whole, ecosystem of the build. In terms of support and training, there is both of them come. I mean, you all obviously have open source tools, and those, are easier to do. But when it comes to bespoke solution, then that bespoke part needs, its own documentation, support training, and it has its own key person, risk, and so on. When it comes to software bugs, because you own most of the, or if not all, of the end-to-end, these are completely yours. And then when it comes to model testing, there is a common element, in terms of results, assumptions, and so on, which is common between the two. But there is also this extra bit now, which is like you have to build your own tooling to satisfy additional requirements, visibility of the code, and so on. Because things are fine when things work, but when they don't work, this is where vendors have spent, for example, some time, in terms of, the metadata they produce, the tooling they use, and so on. Now, these, when you build your solution, you have to cater for that extra bit of functionality as well, and this is what reflects this. But generally, it all boils down to your own capabilities, risk tolerance, strategic priorities, and so on. So there is no one size fits all, and it does not mean that there's definitely not a free meal. There is some cost somewhere. But let's look about versus verbose code. So I've seen there is a trend more code, especially without coding now. But when we look at the history of Actuarial platform, let's talk about the abstraction. Excuse me. Early on, you had frames which were powerful, but they were quite involved and you needed dedicated teams. Later on, you had more proliferated tools that more users could use, as proprietary languages, Excel, VBA, up to this day. Then you had like more general purpose, higher level languages like Python and R, which can also requires some expertise. At the time that this came on, documentation and so on wasn't as good as it is now. Over time, you had other low-code platforms, TSLs, which were optimized for specific domains. Then you had cloud-based platforms and so on appearing. And again, more recently, you have mass entry of vibe coding tool and the barrier of entry to software development dropping significantly. All right, again, it's my personal view on what I believe are misconceptions about when assessing low code versus verbose. So first of all, there is the in my view misconception that low code means less flexibility. That's not necessarily true. When you have a well-designed domain-specific language which provides the full expressiveness of actuarial logic while hiding all the nasty and difficult stuff, then that could be of benefit. So most solutions that you've seen already are low code in the sense that they obscure the infrastructure and they give you actuarial functionality, and then it's up to obviously platform vary in terms of how much flexibility you've got on top of that. So so there is a trade-off between obscuring functionality and functionality limits. So moving on to generic versus domain-specific distinction. So there is a view that generalized low-code paradigms can struggle with actuarial complexity. This is valid for paradigms that have come outside the actuarial profession. But when you have DSLs which are built within the actuarial profession from actuaries, for example, what they attempt to do is draw a line on the distinction between obscuring functionality and providing and exposing actuarial logic. So this is how each vendor see this split. Eliminates the need for coding. So this is not necessarily true, because although the barrier to create your own apps from scratch, has gone down significantly, when it comes to checking, reviewing, and so on, the output is verbose code. So you need to understand how this is done. I mean, the effort to even review it and so on is less because you still have AI. But again, you need some knowledge, and also vibe coding can help and can shine when you have the more complex the case and the bigger the code base, the more benefit you can get from there. But when you have like languages, for example, like Zero platforms, where you can have very concise code, 50 lines of, complex, and you can do that, scratch, how much benefit from using or LLM tools on top of that. There's obviously the question of scale. So that's another thing to consider. So become coders and engineers. Me, this is just I've got a different view. It's like asking, all actors to do their own stunts. So you don't necessarily need to be an expert in all of these. And again, do you outsource it or do you keep it to yourself? So generally, whenever you do it yourself or you outsource that requirement, then again, you need to draw the line between, functionality and implementation. And you have to draw these lines depending on your budgets and so on. So again, these are generic requirements that you have to take into consideration. Next, at Green 13, we've been and we've been living, obviously each vendor cannot be living in a bubble, everyone has to adapt and everyone has to look at new technologies. So our kind of implementation is, we have aimed to, devise a GPU performance, get the GPU performance without the pain. So basically, we have strived to have one single expression language, one model that can run in multiple environments without the restrictions. And you can achieve many thousands of times faster workloads. You can use AI to speed up your transformations. As I said before, we had this use case with 100 products in 20 minutes. You got domain-specific language, so basically, attempting to cut down the burden of having to express models. We have examples where you have up to 45 times less code. Then we wanted to have a balanced technology stack where obviously, as we said, we don't live in a bubble, you have to embrace open source and, you have to allow open source to embrace you. So Iris can talk to open source and can use open source. So again, get the acceleration and be able to run massive models, with hundreds or thousands of output columns and we have examples where we have an ALM where we run 2 million records in about a second, period by period, or you have, term assurances, 1,200 steps, 2 million records in under 1 second, or run 30 million records on a 12 gigabyte RAM GPU, ALM style, so period by period, run it all together, in seconds, so, under a minute, without the need for reruns. So basically, you can use the state and also be fully flexible. So generally for us, the future of Actuarial model isn't about choosing between competing approaches, is to actually intelligently combining them and adapting yourself. But it's all up to you at the end of the day. It boils down to preferences, budgets, and so on. So we can move to Q&A for everyone. Are my contact details if you want. Thank you.